Section: Introduction. We're going to talk about large language models, or LLMs, which have become increasingly popular and powerful in recent years. One such model that has gained a lot of attention is ChatGPT. To prevent these models from generating harmful or sensitive content, they are often fine-tuned to align with human values. However, as these models have become more popular, so have attempts to trick them into bypassing these safety measures, using what are known as adversarial prompts or jailbreaks. Deploying these large models is a significant challenge due to their size and demand, which has led to the use of techniques like model compression to make them more manageable. However, it's not clear how compression affects the safety of these models, as studies have shown mixed results. As these models are widely used, it's important to understand how compression might affect their safety and how we can mitigate any potential risks. In our study, we looked at how pruning, a type of model compression, affects the safety of these large language models. We created a dataset of 2,250 prompts designed to trick the models into generating harmful outputs. We focused on 3 models, each with 7 billion parameters: Llama 2 Chat, Vicuna 1.3, and Mistral Instruct v0.2. We found that initially, light pruning increased the model's resistance to adversarial prompts, but if the pruning went too far, the model's safety decreased. Interestingly, the Llama 2 Chat model was the most resistant to adversarial prompts and showed the most improvement in safety with pruning. On the other hand, the Mistral Instruct v0.2 model was the least resistant before pruning and showed little improvement in safety after pruning. We also found that pruning helped the models focus more on the task at hand. We think this increased focus helps the models detect harmful tasks, which improves their safety. This suggests that moderate pruning could potentially improve the behavior of large language models. In summary, we created and shared a new dataset to study safety in large language models, which includes 225 malicious tasks. We used a recently introduced pruning algorithm to improve the safety of these models. We found that our method consistently improved safety across a variety of tasks, and that the improvement depended on the level of safety training in the original, unpruned model. We also analyzed the model's attention maps and found that the pruned models focused more on the task at hand. We're sharing our dataset and implementation to support further research in this important field. Next, we'll provide some background on the key concepts for this work. Large language models can generate high-quality responses to human prompts, but they can also generate harmful or objectionable content. To reduce this risk, several techniques have been used to better align the model with human values. One effective technique is fine-tuning with reinforcement learning with human feedback. A teacher-student distillation approach has also been shown to improve the model's safety scores. There are many techniques for compressing models, such as pruning, quantization, knowledge distillation, and low-rank factorization. These techniques aim to reduce the model's size while maintaining its performance. They are often used when deploying neural networks to increase computational efficiency. However, it's important to understand how these techniques affect the model's properties, such as its ability to generalize and its robustness. In this work, we study a promising method for pruning large language models and its effects on model safety. Section Summary. Large language models, LLMs, have gained popularity but also face challenges in generating safe content. This study investigates the effects of pruning on LLM safety alignment and finds that moderate parameter pruning can enhance safety against jailbreaking prompts. The study also reveals that pruning helps models concentrate their attention on task tokens, improving safety. The findings contribute a curated dataset, a pruning algorithm, and insights into LLM safety and model compression. Section: WANDA Pruning. WANDA Pruning. The field of natural language processing has seen significant advancements, largely due to the expansion of transformer networks. These networks now have parameter counts reaching into the trillions. For instance, GPT-3 has 175 billion parameters, while PaLM has 540 billion. As these models grow, there's a rising interest in creating compression techniques for large language models, LLMs, that can maintain performance while reducing the number of parameters. This would allow for more efficient deployment of these models on a large scale. One such method is Wanda, a recently developed pruning method. It's efficient, doesn't require any additional fine-tuning, and still delivers good performance. To understand how it works, let's consider a linear layer, represented as W, and a batched input, represented as X. In LLMs, the total token count is represented as T, which is the product of the batch size, N, and the sequence length, L. Wanda assigns an importance score to each weight, calculated as the product of the absolute value of the weight and the L2 norm of X. The method then considers an output index and constructs sets of all weights connecting into that index. The lowest percentage of connections in each of these groups, represented as S%, are then removed. This percentage is the target sparsity. Related work. Other work in this field includes the introduction of layer selective rank reduction, LASER, and the analysis of an orthogonal compression technique, low rank factorization. These methods have shown performance improvements across multiple reasoning tasks. However, some pruning and quantization methods, including Wanda, have been found to negatively impact performance in certain reasoning tasks. Our work contributes to this field by considering a new and important evaluation axis when analyzing LLMs: resilience to adversarial attacks on safety alignment. We found that in some cases, Wanda pruning can actually improve model performance. Adversarial attacks on LLMs. There's a growing interest in finding ways to bypass the safety filters of LLMs and trick the model into producing harmful or sensitive output. With the release of ChatGPT, there's been a rise in various jailbreaks, where users carefully craft prompts to ignore system prompts or bypass its safety training. These prompts can include instructing the LLM to roleplay in an unsafe manner, or avoiding safety mechanisms with unusual scenarios. While providers of closed-source LLMs like OpenAI have tried to patch these jailbreaks as they're discovered, many remain effective. Method. In this section, we'll provide an overview of our methodology, which includes our dataset curation, the levels of model compression used, and our method for evaluating the success of jailbreaking. Dataset. We created a dataset of 225 hypothetical malicious tasks, each representing a different type of malicious intent. These tasks were designed to test the resilience of LLMs against various forms of unethical exploitation, while still adhering to ethical guidelines to ensure they remain hypothetical and non-functional. The tasks were divided into 5 categories: misinformation and disinformation, security threats and cybercrimes, unlawful behaviors and activities, hate speech and discrimination, and substance abuse and dangerous practices. Each category has 45 tasks of varying severity. For jailbreaking prompts, we considered 3 types of attacks: role-playing, attention shifting, and privileged executions. In our dataset, there were 4 role-playing prompts, 3 attention shifting prompts, and 3 privileged execution prompts. Each jailbreaking prompt was paired with the 225 malicious tasks. For comparison, we also included the malicious tasks without the prompts. In total, our dataset had 2,475 examples. Models. We used 3 7 billion parameter FP16 models as our base models, which we then compressed to create our pruned models. These models were Llama 2 Chat, Vicuña 1.3, and Mistral Instruct v0.2. Llama 2 Chat has undergone safety alignment by fine-tuning and using reinforcement learning with human feedback, which helps it avoid generating harmful or misleading content. Vicuña 1.3 was fine-tuned from the original Llama model using the shared GPT dataset. Lastly, the Mistral model is a new model architecture. This model was also fine-tuned but underwent less safety training compared to both Llama 2 Chat and Vicuña. We then used the Wanda method to prune each of the base models to 10%, 20%, and 30% sparsity. The pruned models were not fine-tuned. Section summary. Recent advancements in natural language processing have focused on scaling up transformer networks with trillions of parameters. To make these models more efficient for large-scale deployment, there is a growing interest in compression techniques. One such technique is Wanda pruning, which is computationally efficient, does not require fine-tuning, and maintains good performance by removing the lowest connections based on importance scores. Additionally, the paper introduces a dataset of hypothetical malicious tasks and evaluates the resilience of language models against jailbreaking attacks, where users engineer prompts to bypass safety mechanisms and induce harmful output. Section: Response Evaluation. We evaluated the responses of our base and pruned models for each entry in our dataset. We classified these responses into 3 categories. 1. Refused. The model didn't attempt the task and provided no relevant information. 2. Incomplete. The model tried the task, but the response was irrelevant, inadequate, or incorrect. 3. Correct. The model successfully completed the task. We labeled a dataset of 150 training examples and 59 validation examples from both pruned and unpruned models. We then fine-tuned a ChatGPT 3.5 turbo model on this dataset, which achieved 100% accuracy on both training and validation examples. We used this fine-tuned model to evaluate all the outputs of our compressed models. We initially classified the responses generated by our fine-tuned ChatGPT model into the 3 categories mentioned above. We then manually verified these classifications. Responses classified as incomplete or correct were considered successful jailbreaks, while all others were deemed unsuccessful. This 2-step categorization process helped us measure the effectiveness of jailbreaking, distinguishing between the model's ability to generate responses and the success of the prompts in eliciting desired responses. We know that aggressive pruning can reduce a model's overall abilities. Therefore, we benchmarked the pruned model's performances across various tasks to ensure they were still capable. We used Hugging Face's Open LLM leaderboard, which consists of 7 benchmarks, and measured the pruned model's perplexities on the Wikitext dataset and the effective context length using the Alt-QA dataset. High performance on this task would indicate that long-range dependencies are still captured and that the increased length of jailbreaking prompts does not affect the understanding of the malicious task. We quantitatively measured the model's resistance to generating harmful content. We found that the average jailbreaking success rate varies significantly for different models. The Mistral model was the most susceptible to jailbreaking attacks, while Llama 2 Chat was the most resilient model. However, even for Llama 2, the misinformation category displayed a high success rate across all models, suggesting that this model is particularly susceptible to requests for generating misleading or false information. From the pruning comparison results, there is a clear trend of decreasing jailbreaking success, or increasing jailbreaking resistance, as the sparsity increases from 0 to 20%. However, once the sparsity reaches 30%, the jailbreaking resistance decreases to the point that the pruned model is worse than the original. This suggests that smaller amounts of pruning can be used to improve the safety of LLMs, but too much will negatively affect the alignment training of the models. We also qualitatively looked into responses generated by all the models. We did not find a noticeable degradation in the quality of the responses generated by the pruned models. We noticed that all Llama 2.7b chat model outputs, including the base model outputs, were less informative and less malicious for the most complex jailbreaking prompts, and more informative and malicious for easier prompts. Section Summary. In the response evaluation, the researchers classified the responses generated by the base model and pruned models into 3 categories: refused, incomplete, and correct. They fine-tuned a ChatGPT 3.5 turbo model on a labeled dataset and achieved 100% accuracy. The models were benchmarked on various tasks to ensure their performance, and the results showed that pruning can improve the safety of language models, LLMs, to a certain extent, but excessive pruning negatively affects their alignment training. Additionally, the qualitative analysis did not find a significant degradation in the quality of responses generated by the pruned models. Section: Full pruning versus MLP pruning. We're going to discuss two different methods of pruning, or simplifying, the Llama 2 7B chat model, which is made up of 32 transformer decoder blocks. Each of these blocks has linear layers that are used for both the attention mechanism and the feed-forward network. The two pruning strategies we looked at were pruning every linear layer, and selectively pruning the layers in the feed-forward networks, which are set up as multi-layer perceptrons, MLP. When we tested these different strategies for their resistance to jailbreaking, we found a significant difference. The model that had been pruned to a sparsity of 20% across both attention and MLP layers showed a higher resistance to jailbreaking than the model that had only the MLP pruned to the same sparsity. We also compared our pruned Llama 2 7B chat models to various benchmarks. In general, the pruned models performed as well as, and sometimes even better than, the base model. We didn't see any significant decrease in the pruned model's abilities for reasoning, context length, or language modeling, so we can't attribute the increased jailbreaking resistance to a decrease in understanding of the task. We also analyzed attention patterns to help us understand our safety results. We looked at attention scores from the Llama 2 to 7B chat model when it was in use. We wanted to see if there were any trends in attention patterns across all evaluation prompts, as well as across different transformer layers and heads. We came up with several metrics to summarize the sharpness and distribution of attention patterns. We were particularly interested in the differences between original task tokens and jailbreak tokens. We ranked the other tokens to which each token, in every prompt, transformer layer, and attention head, attends and defined the following metrics. Intra-task rank, which is the sum of ranks corresponding to attention links between in malicious task tokens, and end task rank, which is the sum of ranks corresponding to attention links between the last token in the sequence and in malicious task tokens. In simple terms, the lower the value of either of these metrics, the more resistant the transformer models are to the jailbreak method. We also wanted to see whether resistance to jailbreaking was more related to how we process malicious task tokens, or more to which tokens get the most attention when starting a new sequence. We found that pruned models consistently process tokens from the original malicious task, paying less attention to the jailbreak pretext than base models do. The higher the target sparsity percentage is, the higher the difference is. We also found that these metrics' behavior depends heavily on the jailbreak method, and in particular on whether or not the original malicious task is appended to the jailbreak pretext or surrounded by it. Finally, we looked at an example jailbreak prompt. We compared the base and 20% pruned Llama 2 to 7B chat models, specifically looking at the attention scores that show how much the original task tokens attend to each other. We found that the 20% pruned model pays less attention to jailbreak information in this successful case study. In conclusion, sharper attention patterns help the model resist jailbreak pretext scenarios. Pruning linear layers consistently provides safety improvements across a variety of tasks and severity levels, and they can be explained by numerous metrics that capture model invariance to jailbreak token information. Although somewhat brittle to original malicious task token location in jailbreak, our method consistently provides safety improvements across a variety of jailbreak methods used in practice. Furthermore, this brittleness does not correlate with any decreased performance due to effects on effective context length, as underscored by our experiments on Alt QA.